Department of IIT Guwahati. Before joining this position, he was a postdoctoral research associate at the Control System Center of University of Manchester, UK for 3 years. He completed his PhD in control engineering from IIT Kharagpur in 2018 and did his master's with the same specialization from Jadavpur University in 2012. He received the University Gold Medal in ME and the Institute Silver Medal during his BTech. He recently received also the Young Research Award 2022 from the Institute of Scholars, Government of India. He is an active researcher in the horizon of linear robust control theory, negative imaginary systems, passivity-based control, and dissipativity, cooperative control of multi-agent systems, and control of networked AC microgrids. And this is just to name a few. And I would personally like to share that in 2012, both of us used to share the same classroom to learn AI as well as control. So I'm personally very fortunate enough and lucky to have you, Parijatda, here as the eminent speaker. And we are very much eager to learn the advanced theory and research in your control domain from you right now. So it's now all over to you.
Thank you so much, Pratyusha. Thank you so much for such a kind and brilliant introduction. And I'm really very excited to see you and Anuradha after a long time. Probably it is 12 or 13 years. After 2012, I never got a chance to meet you. So it is
Yes.
really my pleasure to be here. And although this we cannot see each other directly, but still, at least I could see you through online and to Anuradha as well. And really, it's my pleasure, and I'm really grateful to Anuradha for inviting me to this FDP. And I thank you once again to all the organizers and to participants also for coming into this session. My talk I'm going to start now. I have tried my best to just keep the mathematics as much as low as possible because so otherwise the presentation will become very boring. Although it is a 1 hour 30 minutes, 1.5 hour presentation, but this my total number of slides is maximum it would be 48 or 49, and this most of the thing are presentation type in the sense some video clips of the experimental demonstrations and some motivation, new theories, where I insist all the participants that is you please be attentive during the presentation. Don't think that it is highly mathematical or there will be a very hi-fi theory which won't be possible for us to understand. It is not at all like that. But whatever today I'm going to present, it is, I believe there's everything in based on the UG control system, like undergraduate control engineering, which we generally learn in the third year. Even if some of them, if you are not from EE or EC background, even for computer science also, the basic minimum physics, mathematics, and a little bit of signal processing or even signal and system, with that knowledge also, that it would be possible to understand the things. Okay. And one more thing that is, I would insist you to interrupt me whenever you face a difficulty, and I'd really love to take your queries. Okay. With that, I'm going to share my screen, and I hope that is you will enjoy the presentation. Is the screen now visible on the full screen mode?
Yes, sir, it's visible.
Okay. Thank you. And so I'm going to start the presentation. I have kept, it's a generic thing that you must have heard, you might have heard that this cooperative control and multi-agent, this is really a very fast topic. That is, although this domain, the theoretical domain came from control, but if you see the application of multi-agent systems, it has its application in every engineering discipline, not only engineering, even in science, even in finance background as well. That is starting from the applications, like the robotics is the most this eminent application of multi-agent systems and apart from the robotics in like a microgrid, I mean in power system, in power electronics, of course in electrical engineering and in computer science, in biological systems, even in financial systems also, we can apply the theory of multi-agent systems. I think some of those participants have kept their microphone on. Would you kindly put it off? I request all the participants like to keep your microphone off. Otherwise, it will create some disturbance. So anyway, that is with this, the cooperative control, maybe these keywords like cooperative control, multi-agent, it may be just at the as from the title, that is, I gave you a 3-4 line illustration to take you to the slides and which will make all these things clear to all of us. The flow of the presentation is as I just started. The notion of multi-agent systems, consensus and cooperative control. First, just I will show you 2 small video clips and is an experimental demonstration from which these keywords will be clear to you. Then I will come to the formal definition and the concept of what is a multi-agent system, and then how we can model a multi-agent system, and then how we can design a control scheme for multi-agent systems. Then one particular robust control theory, the name of the system, maybe it is not known to many of us because this theory is relatively new. It came into the literature in 2008. Its name is negative imaginary system. At this moment, that is the name might like sound peculiar because when I also heard it for the first time, I laughed a lot. That is, what do you mean by this negative imaginary? But I believe that is once I start, then you will understand the meaning and the interpretation of these 2 words, negative and imaginary. After that, I will show you that is how this theory can be applied to design a cooperative control scheme. One particular application to control of mobile robots, which is the technical name is unmanned ground vehicles or UGVs. And also, I'd like to say that this is the first part of my presentation. That is one more, the application of cooperative control in drones, especially how a group of drones can be applied for border security surveillance or different type of security surveillance. That I am just going to have one more presentation or one more session on 10th. So there, the second part of the presentation will be given. So today, I'll be mostly dealing with the theoretical part with one application, but the major application part, I will be dealing with the next presentation. Okay. So with that, I'm going to play a small clip. From that, you will be having the idea of this multi-agent consensus and cooperative control. Okay. First, like let me play the video and then I will be explaining. Okay. Now, I believe that is you have seen that is the first part of the video, and from that, what are the different information that we can gather? You could see that is here 6 small 2-wheel mobile robots are performing together, right? Now you can think about this. Okay, that is how this experiment is relevant to the talk of this or to the title of this talk. So as you can see, that is when during our undergrad we learned control system or maybe signal and system, then we used to consider one system at a time, right? That is, suppose if you are given a system, either you have a transfer function representation G of S, or you have a state space representation given by x dot equals to x plus bu y equals to cx. And then once the system is known and you are asked to design a controller, we know a different type of controller design techniques. For example, PPI, PID, those things are very common, or even lead or lag compensator, and we used to do that. Now, the question is that if instead of one system, you are given a group of system, then what will happen? And that too, these systems are not operating in an isolated manner. They are working in an unison. That is the now first question, that is which will take you to the domain of multi-agent system. So once again, multi-agent means here multiple systems are performing in a same platform. Okay, so that's why the name has come multi-agent system. So here each system is called an agent. Okay, so in that way, multiple systems are called multiple agent. Now, the one more thing I said that is please don't think that they are working on isolated manner. They are working in an unison. Why? Because they have to achieve a common goal. For example, in this particular experiment, the objective for this six robot is that to start from one particular location and to reach, like if you see this glass bed, this arena, so they have started from the left end and they are supposed to reach the other end of the arena. Okay, and that too maintaining a particular geometric shape where you could see that is it is almost like a triangle, right? And this is a particular geometric shape, and when I will show this, the second part of the video, from that it would be further clear that it is the motion or the navigation, it's not at all haphazard. They have a particular geometric pattern, which also that is has the other reason, that is why they should maintain a particular geometric pattern, or that is what are the different type of patterns which they can make. So this is one particular area which is called formation control. The formation means these agents, they are moving from one place to another by in a symmetrical manner. Okay, and the symmetry or the shape that will be governed by the number of agents and also depending upon the application. So that particular control or that particular phenomena is called formation control. Okay, so now we have learned the first keyword, multi-agent system. Then we have also known that is, since here the ultimate target or the goal is common to all the agents, so that's why the agents must cooperate or synchronize with each other, so that if there is any deviation or the error between two agents, suppose they are supposed to form a triangle, and if they don't talk to each other, or if they don't share their position, velocity, acceleration information with their peers, I mean the remaining the neighboring agents, then there if there is there is an error between the two agents, and the error will go on increasing unless they talk to each other and try to take a corrective measure to reduce that error. So that is the main purpose, or that is the main reason why that is this agent should talk to each other, talking in the sense that is each one of them will broadcast its own information to its peers, and the peers will also do the same thing. And while deciding the control law, it is not that the controller is designed based on the information of that vehicle, it will also take care about the other vehicles. That means here we call it as a relative error. The relative error in the sense that is not only the absolute error. We always know error means r minus y, that is called the absolute error. But in this case, it is not only the absolute error. You have to they care about, like suppose if I talk about the first agent, then that is y2 minus y1, y3 minus y1, y4 minus y1, or even if it is in terms of state, then also you can say that is x2 minus x1, x3 minus x1. So in general, it is xi minus xj. So that is called the relative error. So in a multi-agent system, the each agent must know the position or even the state of its neighboring agents, I mean its peers, so that as a whole they can maintain that, or they can synchronize with each other, and ultimately they can go towards achieving the common goal. That is the sole concept of multi-agent system, and especially this type of control is called cooperative control. Now, why the term cooperation has come into the picture, that I hope that is you have already understood, because here all the agents are required to maintain or they must just maintain a symmetry, or if for that, that is they must talk to each other. Okay, that means if there is any unfortunate deviation between any pair of the vehicle, then immediately those two just must act against the deviation, unwanted deviation, or any kind of error. If it occurs, then immediately they should try to reduce that error. And one more thing, that is often you will hear the term distributed cooperative control. Why that keyword distributed comes? Because in this particular setting, the controller is implemented on a local level. That means each agent has its own controller. So we also say that it is a local controller implementation. It is not that there is a cloud or there is a central server. We are sending all the information. The server will calculate or design the control law, and it will transmit from there, and all the agents will receive. That is called centralized application. Centralized cooperative law can also be designed, but it has one major limitation, the single point failure. Single point failure means that is if there's one agent, this goes faulty, or if like for the temporarily, if it goes out of the network, then immediately what will happen in this like server, when the server is calculating the control law, then it is not getting the feedback from one or two agents. So immediately it will get stuck. So because of the fault or because of the absence of even one agent may destroy the whole thing. The whole thing just may get disrupted and it will be stopped for the time being. Okay, so that is one of the major problem or limitation of centralized control scheme. That's why this distributed control scheme has really become very popular, especially when it is applied to multi-agent system, because it is no longer we are dealing with only one plant, but here we have multiple plants. Okay, so I believe now these keywords starting from is multi-agent system, in cooperation or even cooperative control, distributed control, they all are clear. Only one last keyword, consensus. Consensus means that is if you see the dictionary meaning of the term consensus, it is an agreement. Now, in the literature of multi-agent systems and control, the term consensus is really important, because here whatever the agents are doing, ultimately they should come to an agreement. That is, yes, this is our common goal, this is our objective, everybody must obey this. So in that way we say that it is a consensus based cooperative control. Okay, with that it's starting the video again. Now I believe that is it would be of further interest to you. There is a second part of the video where you will see that is one of the agents will become faulty and the remaining ones will still proceed to finish the mission. I hope that is now you have already experienced that fact. That is this the second part of the experiment. It started with 4 robots, right? Now, unfortunately, after a certain time, one of them has become faulty, so it is no longer able to operate, right? So, but now this is one of the like, advantage of the distributed control scheme. That is, even if that is one that is it went faulty, but the other three will still it will take some time to reconfigure the network, and after some time, that is the healthy agents will take the mission forward. Okay, so that is one of the main advantages of the distributed cooperative control system. I'm going to the next video demonstration. That is, this is about the two-hill mobile robot, and the next one is on the UAVs. I hope that will also be interesting for you. Here, this is called circular time varying formation. Like if you have watch the clip carefully, or then, or even that is like momentarily, just you please see the look at the MATLAB plot. So here, if you that in this particular experiment, we have 4 UAVs or the 4 drones. Now, if you consider the centroid with respect to the centroid, they are continuously that is the moving, right? It is not that they are like standing or they are hovering at a certain position. So of course, like they will be hovering, but along with hovering, they are also maintaining a circular trajectory. So this is called the time varying formation tracking. But here also it's a formation because it's a square formation, but at the same time, that whole square assembly, it's like flowing on a circular trajectory. So this is called circular time varying formation. So once again, I'm running it. Please kindly look into this. Gradually, the drones are drifting from their initial position. And if you see the plot, it's the MATLAB plot, the trajectory, then you will see that it is how they are just moving. This part is even more interesting, where this whole assembly is even like traveling linearly, as if the centroid has moved, and then the whole assembly has also moved. The centroid is usually called the virtual target. That means with respect to which the shape will be determined, whether it's a square or a triangle. Always you need to define a point. It's called the centroid. So that's why that is whenever we design a formation control scheme, always we should have a centroid, which is called if there is no physical target, we call it a virtual target. Or if there is a physical target, then of course it is called a target or a leader. In this particular experiment, there is one, instead of one group, now we have two groups. Okay. So that is fine. With that, then there is now that I will pose a few questions to you. So whatever we have seen, now I believe we have understood all the keywords, right? But now you think about that how this thing can be designed. So that is not at all easy, right? Because both UGV and UAVs, they are all nonlinear systems. And on top of that, UAVs are unstable also. Because as you know, that is for an UAV, first of all, you have to design a controller for a stable hovering. Like all this is UGV, the mobile robot is not an unstable system, but of course, an UAV or the drone is an unstable system. So first you have to design a controller for its stable hovering. That means overall stability needs to be guaranteed. And then after that, for its tracking, or like if there is a point, the drone should fly towards that point, or it should like follow a path. For that also you need a control, or you need a controller. And now in case of multi-agent system, the situation is even more complex because it is not the question of controlling one drone or multiple drones are together. You have to control their assembly, and that too, that is all of them are interacting with each other. That means now it's a problem of a network control system. So that's why often this distributed control system, it has like it is also taught as a part of the network control system, because for implementing any distributed control system you need a network, and all the issues related to the networks, that also those are also very relevant with this aspect. I mean the packet drop or the DOS and all other things, they are also like they cause a lot of trouble here also. So the researchers who work in this domain, they often have to think about those particular aspects also. But in our presentation, that is my sole focus is that how to model this kind of system, and even more than modeling, that how we can design a control scheme for that. Okay, so that is the main purpose. And for that, we'll have to first understand that is that given a multi-agent system, suppose given a group of drones or two-wheel mobile robots, first how can we design that, its mathematical model, and then how can we design a control scheme so that in one hand stability is ensured, and at the same time this formation or consensus, whatever we would wish to achieve as a cooperative control objective, that can also be done. Okay, so with that platform, I'm going to start the theory. Now, first of all, that is, as you have already experienced this cooperative control. So when first this came into the literature, or when this idea like first came up, it is like 30 years before. It was originally consensus control. Consensus control means suppose you have a few agents. Just here, for example, I have considered the four agents, A1, A2, A3, A4. Initially, their positions are like different. They are all haphazardly placed. Now, we want all of them to reach one common point. Okay. Suppose at this moment I am not considering any particular leader, but I want them to reach a common point. Okay. So here this is called leaderless consensus. So what I have just written as a note that this position, the yellow one, it is the average of the initial position of the agent. So this will happen that when we are not specifying any particular location or any particular target. Okay. But from this demonstration, one thing you can understand that is here, this is the meaning of, or this is the interpretation of the technical term consensus. That means, or in a very simple words, you can think about it. Suppose when we learned undergraduate control system, in if I think, or if we have to design a controller so that the output tracks the input, usually we used to say that is okay, output Y, it will track R, right? So now instead of one system, if you have multiple systems, suppose G1, G2, G3, or here A1, A2, A3, A4, you want all the outputs will reach or will track the same input. That means as if that is we are supposed to design a controller so that this Y1, Y2, Y3, Y4, all of them will track R. So now that is nothing but the consensus. That means it is a tracking for multiple systems. In that way also you can like relate it. It will become the very simple in that sense that is there. If you can relate with this our classical tracking, then tracking for multiple systems, that is nothing but the consensus. Okay. So if a leader is there, then it would be leader following consensus. If a leader is not there, then the ultimate position would be the average of the initial condition of the agents. Now, from this diagram, you could have like argued that is here, it seems that is all the agents are operating in an isolated manner. Yeah, if it, had it been in an isolated manner, then this wouldn't have been possible. Even in an ideal environment, it may be possible, but as you know, in the practical environment, always there would be some disturbances, different type of errors, and the other factors which will always cause their motion to drift from the desired one. Okay, so that's why we need the agent to agent interaction. Okay, so that's why this here black dotted arrow, it denotes the communication link. If it is if it can be bidirected, it can be bidirected, or even it can be unidirectional. That means we have like mainly two kind of graphs. One is the bidirectional graph or undirected graph. Another one is the directional or unidirectional graph. Okay, so here for simplicity I have assumed the bidirectional graph. Now as I said, that is if there is a leader or the target, then it would be called a leader following consensus. Okay, the same thing, but here the some target position is given. This is nothing but the tracking. Suppose you have the four transfer functions or four simple systems, and we want all the outputs to reach a common signal. Suppose a unit step signal. So if you can design a controller so that all four systems will reach the unit step input in a finite time, then that is nothing but the simpler problem of the multiple system tracking a reference point is nothing but the leader following consensus. Now the formation control, I believe that it will be very easy for us now because from the experimental demonstrations you have already seen that is what do you mean by a formation. So again, that is I'm starting with the four agents. They are placed in a very haphazard manner. That is their initial orientation. Here, suppose I have assumed that there is either a leader or a target. If a physical target is not there, then it would be a virtual target. With respect to this, that it will like try to go there and occupy their position so that there is a particular geometric shape. For four agents, the most popular or the most convenient geometric shape is the square. So that's why it would be a square formation. Now, as you seen in the video, especially for the drones, that is, if the centroid, I mean, if the leader moves from one position to another, then as a whole, the entire formation assembly will also flow. Okay, so in that way, it will then from one position, it will go into the other position and without disrupting the shape. Okay, this thing is called formation tracking. So first it is a formation control. That means starting from the initial orientation, they will first try to arrange themselves. They will reach the proper coordinate to make that particular geometric shape. And after that, if whenever the centroid, I mean the leader or the target keeps moving, then accordingly the whole assembly will also move, that is without like rupturing their shape. Sometimes that is suppose if unfortunately any obstacle comes into the picture, obstacle or any kind of other disturbances, then momentarily the shape may just get lost. But once that disturbance is relieved, say for example, there is an obstacle on the path of one or two robots, then of course to avoid that obstacle, the robot has to take a different path. So for that time, that the particular geometric shape won't be possible to maintain. But once it has crossed the zone of the obstacle, after that it will again come back to the original symmetry. Okay, so that is about, so I think those who are working on this multi-agent or cooperative control, they all of you just know about this obstacle avoidance, right? So that is one the area within this particular domain. Anyway, that is with that, now you have the sufficient idea about this, all these like the terms specially, and let's see that is like how we can do it further. You might be thinking that is why should we maintain that is the different type of geometric pattern, or that is why this idea or why it came, how or that how was it inspired? Then it was mostly from the synchronization in the nature, synchronization in the nature, or it is also called the nature swarms. You must have seen that is when the flock of birds fly, they just maintain a V shape. For the same kind of what the same kind of thing you will observe for the bees, that is their motion, they will in a particular shape. This the school of fishes, they also, that is when in the very deep sea, they stand together, or that is they swim together maintaining a particular geometric shape. So they all have different reasons. For example, for the birds, that is if they form this V and if they fly together, then it is easier for them to resist the drag offered by the air. So that is one of the reason for the birds flying, birds flocking. And similarly for all other things, especially that in every our there is a house or in our home, that during the every rainy season we see the movement of the plants. Sorry, we see the movement of the ants. You must have seen that is the ants, they always maintain a queue, right? And which is called the leader follower structure. That means the one agent, that is one ant will, or every ant will always follow its predecessor, right? And then the successor will see its next. In that way, that is, they always maintain a line. One line would be for this going from one destination to other. At the same time, you will find one line is coming back. In that way, that is, the small creature or insects, they take the different kinds of cooperative motion or cumulative motion so that they can survive in this world, and also they can make their things done, because as compared to human being or all other the large creatures, they are really very small, right? So they, if they can't take any like the measure against the nature or against the cruelty that is by the other bigger animals, then they would have extinct, right? So that is some of the reasons, that is why we see all different type of that is swarm active cooperation in the nature. So with that, there is a complete different subject which is called bio-inspired swarm, or the swarm algorithms which are completely bio-inspired, starting from the PSO, SEO, BCO, all those kind of things. Though who are working on the soft computing or the artificial intelligence, they are very well versed with that. Although I don't work in the like bio-inspired swarms, but I should mention that is the main reason or the motivation behind this cooperative control. It originally came from the nature swarms only. Now, the first question is that given a problem, like suppose in an industry or in a factory, that you have some robots and which will be performing some operation. You can think about that automated car manufacturing industry. There are some particular tasks are to be done by a few like robots. You can be humanoid robots, or even you can think about the robotic surgery, where there is three or four arms would be doing a not minimally invasive surgery. So how they will be controlled? But even before we think about their control aspect, we have to first model them, right? So that's why the first question in the cooperative control literature is how do we model a multi-agent system? Whenever this comes into the mind, especially about the modeling, then even before that, we have to think about that how do we model the interaction among the agents? Because anyway, when you have a physical system, that is either you can write its the differential equation, I mean the physics-based modeling is possible. If it is a too much complicated system, suppose physics-based modeling is either not possible or even that it is going too much complicated, we always have the input-output modeling. I mean the black box approach from from the experimental data, you can use the machine learning techniques to get a based on the input-output data, you can always get a model, right? So either like the white box detail model or the black box model, that somehow that is will be able to get. But now the question is that how about the synchronization? How can we model the interaction among the agents? So for that, actually, I have taken two very small examples of the only three agents. The first one is for the leaderless consensus, so there is no leader, and the second one there is one leader, which is called the root node. Okay, and now what we need here, that is, we should like recap our concept of Laplacian matrix, because in designing the control scheme, especially this, if we have to design the cooperative control scheme, we need the Laplacian matrix of the graph. Okay, so the first graph, we have three agents and they are communicating to each other. It is since both arrows are there, that means they are bidirectionally connected. Their weights are, like, since they are bidirectionally connected, so I have assumed that is the both the outward and inward weights are the same. So A12 equals to 21. Similarly for A23 equals to 32 and 31 equals to 13. Please note that if it is a unidirectional communication, that means if it is an undirected directed graph, then there will be either A12 or 21, okay, not the both. And usually, that is, if there is no priority setting, we can simply assume that is whenever two nodes are connected, happens here in the, when we are going by this, here we are applying the graph theory for the modeling. So in that literature or in that notion, we consider each system or each agent to be a node, okay? And the edge connecting two nodes, actually it represents the interaction. And simply you can consider that is Aij equals to 1 if two nodes are connected. That means if two nodes are interacting, or it is 0 if they are not connected through a network. Okay, so with that, we are going to define, or we are going to find out the Laplacian matrix. If you have forgotten the Laplacian matrix, then we can easily remember the Laplacian matrix of a graph is the subtraction of to another matrix, which is D in. D in means the in degree matrix, and A means the adjacency matrix. Let's see, that is how we can do that for this particular simple example. So as you can see here, each node in degree means how many incoming nodes. So the agent one, that is, or not only agent one, here all three agents, they have, that is the two incoming nodes, right? Each one of them, they, since they are bidirectionally connected, so for each one, they have two incoming nodes. So that's why the in degree matrix for all three nodes would be 2. So that's why the D in here is a diagonal matrix of all the diagonals being 2. Now the other one, adjacency matrix. Adjacency matrix means this actually represents the interaction or the weights here, all the here. Sorry, here should not be minus. I'm very sorry for the typo. They will be all 1, but after this minus, finally it would be minus. Okay, so please excuse me for that. In the adjacency matrix, it actually gives, it consists of 0 and 1. 0 means there is no connection, and 1 means those two nodes are connected. Let's see, that is how I have constructed it. So first element is 0. So if you can read this matrix as if this is node 1, 2, 3, like row wise and column wise 1, 2, 3. So first one would be A11. That means the weight associated with the edge 1, 1 to 1, but no self loop is there. So of course A11 would be 0. The second one, A12. Let's see, that is if it is there or not. Yes, that is 1 and 2 are connected and bidirectionally connected. Bidirectionally connected means 1 will get the information of 2. At the same time, 2 will also receive the information from 1. Okay, so that is the meaning of bidirectionally connected. So A12 would be 1. Similarly, A21 should also be 1 because both of them are connected to each other. So A12 and 13, both of them are 1. Now, let's go to 13. That is there any connection between 1 and 3? Yes, the connection exists not only from 1 to 3, from 3 to 1 itself, 3 to 1 as well. So A13 and 31, both of them must be 1. Yes, that is there. Then we'll have to consider the connection between 2 and 3. Yes, again the same thing, 2 and 3. both of them are connected to each other. So A23 and 32, both of them would be 1. So they will also be 1. But as no self loop is there, so A11, A22, and A33, all of them would be 0. So we can see the diagonal entries of the adjacency matrix are all 0. Finally, if you find out the resultant matrix, it would be 2 minus 1 minus 1 minus 1 2 minus 1 minus 1 minus 1 2. Why I'm reading the value wise? Because it is one of the major property, very interesting property. Whenever we deal with undirected graph, their Laplacian matrices are always symmetric in nature. Not only symmetric, they are positive semi-definite. That helps us a lot in designing a cooperative control scheme. Okay. Now, the same thing that if you wish to find out for the second case where there is a root node, that means there is a leader which would be tracked by the agents. Okay. So that means now you have a generator node which is called the root node. So the root node is attached to the agent 1. So now in terms of in degree, you can think about that it in degree, like I mean the in degree of agent 1 is going to increase by 1 because it has one more node. Okay. So that's why here often it is defined as a pinning gain matrix. Pinning means here the root node is pinned to agent 1. Okay. So it is a diagonal matrix of you can read it like the P1, P2, P3 up to Pn. P1 means the gain between the root node and the agent 1. P2 means the edge or the weight of the edge connecting the root node to the second one. Similarly, P3 means the edge connecting the root to the third agent. But here, the root node is connected only to the first agent, not the second and third. So that's why the second and third diagonal entries of the second matrix is 0, but the first one is 1. So if you add this one, then it is, you can say that is a L plus P. Now that will, of course, it will retain its symmetry property, but now it is no longer positive semi-definite. It is now a positive definite matrix. Okay. So that is the main advantage when we design cooperative control scheme for undirected graph. This property like L plus P is a positive definite symmetric matrix. It helps us a lot in designing the control scheme. Okay. Here I must mention, although I haven't prepared a slide on that, if you have a directed graph, then provided there exists a spanning tree, then this Laplacian matrix that also has an interesting property. Although for directed graphs, the Laplacian matrix will no longer be symmetric, but it will be an M matrix. M matrix means it's all the off-diagonal elements, they would be non-positive and the diagonal elements would be non-negative. And ultimately, the real part of all the eigenvalues would be non-negative. Okay, so that is the properties. Those are some of the properties of the M matrix. So for the directed cases, so that's why if you see any like literature on the cooperative control on directed graphs, then this spanning tree condition is a necessary condition. So in each and every paper, you will find that is this spanning tree condition will of course be mentioned, because without which we cannot proceed with the controller design. Okay. So as I said that for directed graphs, that is we use the graphs with having spanning trees so that the Laplacian matrices have they exhibit the M matrix property, and so that at least even if they are not symmetric, but at least their eigenvalues will all be in the right half plane. Okay, so those properties are required for the controller design. Let's take an example. Like suppose in a security surveillance system, in one floor we have deployed 4 drones. Okay, they were covering or they were mapping one particular area, and each one of them is communicating to the remaining all. So in that case, the Laplacian matrix would be like this. So here again, you can read about that is the first one is the that is completely it is a 3 means now if you it has the in degree plus
Sir, sir,
yes.
sorry to interrupt. Your screen is not visible, sir.
Is it?
No,
Is it
sir.
now visible?
No, sir.
Maybe there is a like problem with the internet.
But I'm able to see. It's visible for me.
No, actually, I am seeing you, sir, not the screen.
Oh, then you'll have to share the screen, sir.
No, the screen is already shared.
So may I request you to stop share and
Ha
reshare
ha
it
ha.
1 second?
Ha.
Reshare it 1 second, sir.
Yeah. I hope it was fine
Hello?
even 1 minute before, right?
Yes, sir. Yes, sir.
Okay, so then I think momentarily there is a problem. But here but still I couldn't find the share button. It is only like showing that it is deactivated.
You
Just
need to
let me.
ask for the permission from the organizer. She will can give you the permission to share.
Okay, because since it has already started, right?
This is, right now, we can't see anything on the screen.
Huh, so I need to stop share, but I don't have the permission to stop share.
Sir, just a minute, please.
Huh. Would you kindly give me the permission to stop
Sure,
share?
sure. Sir, just give
Huh.
me 1 minute.
Sure. I'm really sorry about that. I don't know that is how it occurred.
So I request you to kindly relate the last few lines with the PPT so that we can have a.
Yes. Sure.
Thank you so much.
Hmm.
So, will you please once share it once again?
Yeah.
It's visible now, sir.
Huh.
Just, I will request you, humbly request that just maximize the screen.
Yes. Sure. So how far have you been
Sir,
able to listen
may I
to?
ask one question here, sir?
Please.
Sir,
Sir,
how you put these values to diagonally 2. And the second matrix is the weightage, I think, the
So
relation
this is
between.
about the in degree. In degree means how many incoming nodes for each of the node.
Hmm.
So for the first agent, you can see there is this bidirected
Okay,
graph.
okay.
So
Yeah.
3 and 2. So that is the thing. Okay.
Okay.
So it is a symmetric graph. So that's why there is all the entries are 2. But if you can think about the other type of graphs also where the entries would be different. That is, if the in degrees are different, then of course the values would be different. Okay. So, but I hope that is this slide where where you all of you listen to the full explanation for this slide.
Yeah.
So now I think that is from here it was a problem, right? From slide 11. Okay, that is just I'm starting from this only. That is now it is for the security surveillance. Suppose that is you have either that is in the parliament or in a shopping mall or in any other kind of office, instead of that human surveillance, if it is the automated surveillance. So for that we have to deploy a group of drones. Just for simply here we have 4 drones. They are this covering one particular area. Now, if we design the network in the sense, or if we design the cooperation in the sense that is all the agents would be like talking to each other, particularly in this fashion, that is here all these arrows they are pointing out that is which two or how they are communicating, then its Laplacian matrix would be like this what I have written. Okay, so this is a particular one where I didn't consider any target. Okay, so that's why the pinning gain concept won't be coming here, but all the like weight factors like in degree matrix and the adjacency, they will all be here. So I believe you can easily relate that except the diagonal entries, all the remaining ones would be -1 because each one is connected to the remaining ones, right? And now what about in degree? That you consider any of the agent, they are connected to the 3 other agents, right? So that's why the in degree is 3. So that's why that is this from the Laplacian matrix. Again, that is it's a like a balanced one. So for that is you all the entries or especially all the in degrees are the same, but it may not be. Just to take an like the easy thing that is I have shown that this particular thing for convenience. Another example, which maybe like from that your the further doubts would be clear. So suppose the fighter aircraft, the choppers on a mission. Okay, this bigger one, suppose it's a leader, and the remaining ones are the follower. So the leader would be interacting with each other. So the leader means actually it will transmit its own information, and the remaining ones would be like following him, but he is not following the other. That is that's the meaning of the leader and the follower. Okay. So now among the followers, if you see that F1, F2, F3, all of them are pinned to leader. That means all of them are receiving the information from the leader. So the pinning gain matrix would be a diagonal matrix containing all ones. Okay. Now, as far as the Laplacian matrix is concerned, here you can see this is LP. So LP means it is L plus P. So as I said, here the spinning gain matrix will become a diagonal matrix of all ones. And now what about the Laplacian? Laplacian, again, it would be in degree matrix minus adjacency. For the adjacency, as you can see, that is this, the second agent is connected to the first one. At the same time, the second agent is connected to the third agent. Okay, but not the vice versa. That means the third agent is not getting any information from the second one. And the first agent is also not getting any information from the second one. Okay. So that is the reason. That is why there is the wet for A12, that is the entry 1213 and 3132, they all are 0. Where we have the 21 is a 1. Why 21 is a 1? Because 2 is getting information from 1. Similarly, please stop your microphone. I sincerely request, please stop your microphone. I'm really sorry about that. And now that is for similar to 2, 1, you can also think about the 2, 3. So that is the 2 is also getting information from 3. So that's why this weight is also 1. So that is that type of example I wanted to give you. Like since it has the directed communication technique, not by like bidirectionally connected. So it is not that A12 means A21 also. It is not that A23 means 32 also. So only here the 2-1 is 1 because 2 is getting information from 1. At the same time, A23 is also 1 because 2 is getting information from 3. But A31 is 0. A12 is also 0 because they are not getting any information. Okay. So similarly, 3-1, 3-2, they are also 0. I hope that is now that you have a clear-cut idea about this Laplacian matrix. Then that is what we were intending to learn. It is the graph theoretic modeling of a multi-agent system. Like we have now that is understood that is how the agents, how the interactions can be modeled. Then after that, how we can model this whole system, including the interaction. So again, here I have considered, like suppose you have a root node and we have a group of agents that can be 5, 6, 10, 15, 20. That can be represented in this way. Suppose the dynamics of each agent is denoted by M. So MS, if it is a LTI system, it is possible to write the transfer function, then you can always write it as M of S. But suppose if it is not an LTI system, non-linear, so writing the transfer function is not possible. So you should represent only a system only by its name. So that is the purpose why I didn't write M of S in this bracket. Okay. So here M up to, suppose if there are n number of agents, then it's a stacked version of all the agents. Okay. So it's a diagonal matrix, then as if that is we have packed all the isolated agents. But you might have readily encountered that it is multi-agent system means it is not the collection of isolated agents. There are interaction. Yes, of course there are interaction, but mathematically we can decouple that interaction. So this is the interaction that is modeled by a graph, and that graph is characterized by a Laplacian matrix. So mathematically means by applying the concept of conical algebra, conical product, we can always, like mathematically, we can segregate the plants and the interaction. So that's why now as a whole, one multi-agent system can be represented as a cascade of this Laplacian matrix as well as the isolated plant dynamics. Okay, so that is overall the mathematical representation of a multi-agent system. Let's see, after this, that is now we have the idea about this structure. Then we have to dive into the part of this presentation, that is how can we design the distributed control scheme for multi-agent systems. It can be of two types, the state feedback based and output feedback based. we can easily relate with our classical control concept that is there when in our like the fifth semester or even in the fourth semester when we had the control system one, that is the control system engineering in the first subject. Then we learned about the PID controller or even the lead lag compensator, right? If you remember the PID controller or the compensator, every time that is we used to place the controller on the forward path. And what is there in the feedback path? It is simply unity negative feedback, right? I hope now you can remember, all of you, simply unity negative feedback. That means they are all output feedback based. That means here the control law or the controller, whatever we design, it depends only on the output feedback. Contrary to the modern control aspects. In the modern control, that is when we learn the state space. Then here, instead of only taking the output feedback, if we can apply the full state feedback, that means in addition to the output, if we can also keep a constant eye about the internal dynamics of the system, that means the state also, then we can apply or we can even expect even a more grip over the system. So that's why the concept of state feedback this came into the picture, which is the part which are taught in the modern control. Okay, so with that concept here also, I'm going to show you that in case of multi-agent system also, we can design a distributed control scheme based on state feedback as well as based on output feedback. Okay, both of them, they have some pros and cons. In some applications, state feedback are better. In some other applications, output feedback are better. So let's see, that is the overall architecture. Now, if you see this block diagram, the blue dotted, the rectangle, then this represents a network multi-agent system, right? And we have to design a distributed controller. Here, although I have like written the Y, so you may have a feeling that yes, it is output feedback based control, but easily you can think about that instead of Y, if I write X, then all the states would be available. That means the one block diagram, it can represent the output feedback scheme or even state feedback scheme. The only change that needs to be done is that instead of Y, we have to write X. Okay. The main question is that how can we design this control law? Of course, it will depend upon the agent dynamics, which is M, and the graph properties also. Why graph properties? Because in the graph, it is characterized by the L. So if it becomes, suppose if it is an undirected graph or if it is a directed graph, and whenever it has a lesser number of edges or even more number of edges, of course, the L will be different. So the eigenvalues would be different. Accordingly, the whole plant will also change. That is, you see the entire block of the network multi-agent plant. This is nothing but the L into this whole block M, right? Now, if L is different, that means even if there is a small change in the graph, then the L will be different. So, of course, the plant dynamics would be different, right? Because it is not only about the only dynamics of the plant. Now, the as a whole multi-agent system, it depends highly on the Laplacian matrix as well. That means the graph plays a major role in a multi-agent aspect. Okay, even if like there is a change of only one edge or even there is a reversal of a direction of one edge, then also the L matrix would be different, and then which will make the multi-agent plant a little bit different. Okay, so that's why really we have to be careful about the modeling part. Okay. So now these are some of the control objectives which we have to keep in our mind before just going to the controller design. The red highlighted two, the first 2 points, they are very essential and they are the just a major objectives. That is, first of all, as you know, for in any case of a controller design, the overall stability must be ensured, and then we have to think about the tracking. In terms of multi-agent system, we don't say it's a tracking, rather we say it's a consensus. So first one to ensure the stability of the overall network system, and the second one to ensure that the agents reach consensus. If it is a formation control, then they should achieve the formation. Okay. The last but not the least, the other aspects are also there. That is, once this consensus is achieved and assuming there is a stability is already there, you have to take care of the uncertainties, disturbances, noises, and the network issues, like will always be there whenever a network is involved, and also some other type of problems. Okay, so these are some of the major objectives. Although in today's presentation, that is, we will be restricting only to the stability part and the consensus. Now, this is the first scheme. That is, you please like pay your attention on this slide and try to match. That is like, what is the concept? So now this is the multi-agent plant. This is the network part. So here you must have noticed one difference. That is, earlier it was only L, but now I have written L plus P. Why? Because the reference is also in this picture. Earlier there was no reference. That means the leader was not there. The moment you consider the leader or the reference generator, so of course the question of the existence of the pinning gain matrix will be there, right? Because the one leader is there, that means it must be pinned to at least one of the agents. So that particular gain would be there. So we have to include the P matrix with L. So that is the reason why here I have denoted by L plus P. So as a whole, you can think about that the whole scheme, that is, as I have this red dotted ellipse show that this is a distributed state feedback cooperative control scheme. Now, similar to the classical state feedback, that means there is a gain, this K matrix, that is our main concern. That is, we have to design this K matrix so that this entire loop remains asymptotically stable, and also the steady state error goes to zero. The steady state error goes to zero means finally all the agents will reach the consensus asymptotically. Okay, that is the overall scheme. Now, of course, like from that, you may face a little bit difficulty in the sense that is how that is could we think about that, or how like could I draw directly this block diagram? For that, as a backup, that is I have like included like two slides which will like take you to your that is the undergraduate days. Like let's like recap the concept of state feedback. We can remember the concept of state feedback where the law is given by r minus kx. How? Suppose you have a very simple double integrator system, 1 by a square. So the first state would be the position, and the second state would be the velocity, right? So here for this particular system, we will have two states, x1 and x2. And then the state feedback control law can be written in this way. That is, here the u, that is r, the reference, minus k1 x1 minus k2 x2. Basically, this is the compact form, r minus kx. So now I think you can relate. That is, if I just go back to this picture, here also you have a multi-agent plant. And then similar to the classical control scheme, you should have one K matrix, which is the state feedback gain matrix. This C, you please don't like take any pressure regarding C. C is C, or sorry, there is a typo. It must be sigma. So this is like the scaling factor or the tuning factor. So at this moment, you can simply skip that the scaling factor. So the K must be designed, but the only difference is that earlier we didn't have any L matrix. That means when as long as we are dealing with a single system, then there is no question of this Laplacian matrix. And now in case of the multi-agent system, of course, the Laplacian matrix would be there. So the plant is no longer is only the collection of the transfer functions of the individual agents, but the network part will also be there. So as a whole, we have to design this K matrix. Okay, this is the aspect. And so now that is, if you would like to know more about it, then like how does the distributed state feedback control law works, then I have included this slide. I think that from here, it would be like evident to you. Again, the same example I have taken, we have three agents, G1, G2, G3. They are bidirectionally connected. Okay. Then each system has its state x1 and output y1, similarly x2, y2, x3, y3. Okay. So now the distributed state feedback means you just in the previous slide, you have seen that is r minus kx, right? So if you remember that in the beginning, I said that is while we wish to control one system, then we always look for the absolute error, that is r minus y or even r minus x, because if it is a state feedback control, then it would be r minus x or even r minus kx. But the moment you step into the multi-agent domain, then it is no longer the error with respect to the self. Here we have to consider the relative error. I mean, of course, the absolute error, r minus y or r minus x, but at the same time, you have to consider the error with respect to the neighboring agent. So that's why now the control law will take the form that is K, that is the gain matrix will definitely be there. Now x2 minus a12, that is the weight of the edge. Suppose if it is simply connected, you can read that a12, 31, they all are equals to 1. So the u1, that means the control action which, or the control input which will be fed to the plant, it will depend upon the relative error with respect to the other two agents. So that's why what is the relative error? With respect to x2, the relative error is x2 minus x1. And with respect to x3, the relative error is x3 minus x1. So as a whole, what is the summation of the relative error or the cumulative relative error? That is x2 minus x1 plus x3 minus x1. And you cannot neglect the self error or the absolute error. So r minus x1 will always be there. Okay. So as a whole, this is the total error. And the controller is here. The controller means that state feedback gain matrix that will work on the total relative error. So that is the difference between the cooperative control and the single agent. For the single system or multiple system, that is the difference. Once again, you can relate, that is earlier we had only u equals to r minus kx. Okay, but now the situation is that it is not about only k into r minus x1, but also that is the others, there is a relative error with respect to the neighboring agents. Okay, so in a compact form, we write this particular, you can, if you like simply expand for suppose I equals to 1, 2, 3 and j similarly 1, 2, 3. For you, if you write u1, u2, u3, you are going to get the same expression. Okay, so now suppose I think that this will help you to understand the background of a distributed control scheme. So it is not a big deal. Only thing that is you have to think in terms of the neighborhood error. Neighborhood error means that is when one system is moving, it must also check that what is the error with respect to its neighbor. And its controller, which is the local controller, will be acting on the error, not on the absolute error, but on the relative error. Okay, so that is the pair. So in that way, now I believe that is this will that you will find it like really useful, and also it is now not that tough, which it seemed to be at the beginning. So coming to the distributed output feedback. Output feedback means now you can easily like see that is here instead of the states, we are now dealing with the output. Okay. And here I have assumed that is either linear plant or linearized plant. So that's why I have written M of S. So now the main question is that we have to design the N of S. That means the controller. Okay. And as a whole, that is whatever like controller that is we choose, we have to first show that yes, this entire closed loop control scheme remains asymptotically stable. So here also you can think about that this is a multi-agent plant. So this is a network part, and that we can think about that this network part, it can be either clubbed with the plant or it can be clubbed with the controller, because these are all mathematical representations. So, okay, so if you consider or if you club the network part with the controller, then it would be called a distributed controller. Okay, so that is the meaning of the term. So only thing, the difference between these two schemes, the one uses the state feedback, the other one uses output feedback. And the second difference is that in the first case, it was just a static controller, right? If you remember that there was no dynamics, it is simply a static controller K, but the scheme which we just seen, there we are dealing with a dynamic controller. Okay, so actually now that is gradually we are going to learn and how we can design this dynamic controller given a multi-agent plan, because otherwise the entire theory that is would have no application, right? Because given a multi-agent plan, we have to decide or we have to design this NS. Okay. Now the same block diagram which we here I drew, it is rearranged into this fashion. Why? Because right from the beginning, that is we have been familiarized with the block diagram, that is everything is present on the forward path. That is, if you just remember the classical control scheme with the block diagram that we used to read from the Nagraj Gopal's book or Ogata, that is, there is a reference, then after that is a summer, the error signal, it goes to the PID controller or the controller in the forward path, after that the plan, and the loop is closed by a unity negative feedback, right? So here we are familiarized with the everything being placed in the forward path. But unfortunately, in this diagram here, that is, we may have a feeling that is okay. Here the forward path means the plant is there, even the network part is also there. But unfortunately, the controller is on the feedback path. But it is certainly not. Why? Because whether it is a forward path or feedback path, you have to check with respect to the input and the summer and the output. So if this is the starting point, so this is the summer, this is the input, this is the starting point. So if I start working on this line, so then this is the first block I encounter. After that, this is the second block. After that, this is the third block, and this is the Y. So, and this Y is directly going there. So here also, that is the after this Y is going to the summer block. That means there is only one I. That means that identity matrix, unity gain. So although this has been drawn in a different manner or in a different fashion, but it is here also all the blocks are on the forward path only. So that's why that is initially when I did it. So I also faced the same type of doubt. That is, are we now placing the controller on the feedback path? So is it going to be different from what we have learned in our classical control or even during our undergrad? So it is certainly not. So that's why that is I have redrawn that block diagram. There is only one trick I have played here. You can see that is the controller is coming before the plant, right? Or even the network block is there. So that is that part I have done over here. The trick is that for the analysis purpose, you can like swap these two blocks as well by using the Kronecker algebra. That is not also a big deal, okay? But here at least this is just a rearranged block diagram. Why did I did it? Now you can easily relate. So this is for this reason only I wanted to represent in this fashion. That is, we are always in our mind, we had that structure. That is, there will always be two blocks. One stands for the plant, another stands for the controller. So if that is one is GS, another is CS, the transfer function will be GS divided by 1 plus GS. And then we have to find out the characteristic equation to check the stability of the closed loop system, and like so on and so forth, which we learned during our undergrad. So just to like give you that feeling, that is, yes, like now we are going to an advanced state, but essentially we at every step we can relate with our classical control concept. It is not that we are learning multi-agent means it is a rocket science. It is not at all. The only thing that is how do you look at it, or how do you like see all the things. So that was the main intention of my talk. That is, I wanted to place everything with respect to our undergrad concept. That is, here also we have two blocks, although that is we can see three blocks, but the controller and this L plus P, I mean the network block, together they form the distributed controller. Okay, so essentially here also we have two blocks, and if you see my marking, that is this one red block and one dotted blue block. So one is the plant, another one is controller. The same thing which we learned earlier, that is we have a controller block, we have a plant block, with only difference that is now either the plant or the controller will contain the network, but I mean the L plus P. Okay, but when that we are after this, we will be like stepping into the stability study. For stability study, we have to study the stability with respect to the interconnection of two blocks only. We are not going to consider three block. Okay, so in that way, that is you can feel yourself, or you can like rest assured that is whatever we learned during our undergrad, the same type of concept are applicable here also. That is, after this I'm going to show you that is this consensus can be proved simply by showing that the steady state error going to zero. That is, you don't need to like bring in very hi-fi kind of theory to show that is this consensus, whether the consensus is achieved or not. And just for a recap, what are the primary cooperative control objective? The first of all, the closed loop network system must be stable and the tracking error must go to zero. Okay, the tracking error goes to zero here. That is, although here is a zeta and the e the same thing. Okay, that please don't mind for using the different signal. But ultimately we have to see, or we have to show that the steady state error goes to zero. That means the steady state output will reach the R. Okay, that means as if you can, as like right from the beginning I have been mentioning, that is this the cooperative control or the reaching consensus, you can always compare with the thing that as if multiple systems or multiple outputs are trying to reach one common reference, suppose a unit step input. Okay, so in that way you can relate. Now the question that we are going to the main part, that is how to design a distributed controller. So it is $1 million question, that is how to design a distributed controller, because if you think about the class of plants, then there are infinite possible choices, right? It can be linear, it can be linear time invariant LTI, it can be linear time varying, it can be linear parameter varying, non-linear, and in each category there can be a number of plants or even infinite number of plants. So we cannot expect one very particular or just one common scheme which can be applied to all possible type of plants. It is like impossible. So what we can do instead, that is now for different type of plants, say for example the stable LTI systems or even unstable LTI systems, or suppose like linear stable LTV systems. In that way, if we can group certain plants, or even within LTI systems also, if we can partition the whole LTI class into small subset, and then for each subset if we can propose one architecture, that will also be very helpful. So the one thing you please rest assured, that it is not possible to come up with one particular unique scheme or universal scheme of universal cooperative controller which can be applied to all type of plants. That is not completely impossible, but if we can at least find out 10, 15 or like 20 different type of cooperative control schemes which will cater to small subsets under the LTI plants or some of the nonlinear plants, that too will be a lot. Okay, so actually when this research started, this graph theory based cooperative control, it was first proposed by Professor Richard Murray, Caltech, in 2004. From actually starting from 2003 and 4 onwards, like this concept of the cooperative control, especially the consensus graph theory based cooperative control, it started. Earlier also cooperative control exists, but at that point of time it was not distributed cooperative control. It was mostly centralized cooperative control or even centralized control for multiple systems. And in most of the cases, they used to be designed by the other methods, not the graph theory based modeling. Graph theory based modeling means there is this interactions are modeled by algebraic graph. So in this whole block diagram or in this whole scheme, this Laplacian matrix will be included and it will take a major role. Okay, so that is the main essence or the main property of a graph theory based cooperative control scheme. So if you see the earlier literature, then the first 5-6 years, starting from 2003, 4 till 2008, 9, or even 10, most of the pioneering work on literature on cooperative control were devised for multiple integrator system like single integrator, double integrator, or higher order integrators. Now you can be very like at this moment you can be very disappointed, or you can ask that is, oh, there is very simple, that is first order, second order, second order integrator, or even the higher order integrators. What is the point of that, or why those like early people, or why the forefathers of cooperative control did only for these multiple integrator systems? The reason is that is this 1 by a square, the double integrator. It seems like very the small, or it seems very, what should I say? That is, it is not, it doesn't have that is at all worth, but it is the most essential or most interesting physical system. Why? Because whatever type of linear motion or rotary motion you think about, like most of the things will be governed by Newtonian mechanics, right? By Newton's like third law of motion, that is the which would be the in the formula form, it is the force equals to mass into acceleration, that is f is equals to m into a. Now you like take out the transfer function, f of x equals to the mass constant into then acceleration means the double derivative of position. So after taking the Laplace transform, what it is going to be, f of s equals to m into s square. S means the Laplace variable s into the position of s, suppose y of s. Then what will be the transfer function from force to position? Y of s by f of s is equals to 1 by ms square. So that was the main driving factor, that whatever motion you model, That is ultimately, that if the transient part is left, or if the disturbances portion were left, then at the steady state motion, whether it's a linear or rotary, that either the force equals to mass into acceleration, or this torque equals to the j into theta double dot or j into omega dot, both these equations will give us a double integrator mapping. So that was the main reason why this kind of cooperative control, which was first developed for interacting small vehicles, that means this kind of two-wheel mobile robots and the other thing, that is a small like elements which are interacting with each other and they are moving towards achieving a common goal. Their motion used to be captured or can be approximately modeled by double integrator system. So if their approximated dynamics is governed by double integrator system, then how can we develop a cooperative control scheme so that multiple double integrator systems can reach a particular point? That was the original motivation. Okay, so those few papers, if you just study the literature, then you will be seeing that all those things were mainly developed by this 1 by s, 1 by s square, all those things. Okay, so now for that, like since I'm going late, I'm just going to like end quickly. So the thing is that as I said, that is this kind of systems, or we cannot expect one universal scheme, that is for the universal scheme for the cooperative control scheme for all possible type of system. It is not at all like possible. But rather, if we have different classes of system, for example, finite gain systems, which are the class of asymptotically stable linear systems, if we can think about the passive or positive real systems, if we can think about negative imaginary systems, such kind of theory that is will just give us or for this kind of sets or for this kind of subsets, we can design some cooperative control, particular cooperative control law, which gives really very good results. So with that, actually, that is going to just dive into this. And here, one more thing, that is what I wanted to show you, that is the last bit. That is, here are three. So you can think about, or you can ask, that is the presentation of flow. That is, I mentioned, that is, I would be dealing with this mostly negative imaginary system. But what's wrong with the other thing? That is, can't we apply the others? Yes, we can like, apply the others. But if we have to deal with integrated systems, especially like 1 by s, 1 by s square, or even just multiple, then finite gain systems, as I just mentioned, they were the class of asymptotically stable system. So 1 by s or 1 by s square, they are not asymptotically stable. So the first theory cannot deal with integrator system. The second one, passivity based theory. 1 by s, single integrator system is a passive system, but double integrator system is not a passive system. Passive systems cannot consider the double integrator system because the definition it holds. So the passivity based theory, it cannot be applied to double integrator system, but negative imaginary system, it can accept up to two poles of the origin. Here also, that is, if you think about the triple integrator systems or even further, 1 by s to the power n, that we cannot directly apply, but at least for single integrator, double integrator, and many other type of vibrational control system, we can apply the negative imaginary theory. So that's why that is that my next plan is that there is a, yeah, I would be dealing with the negative imaginary system theory. Of course, today I don't have the time. So the next day, that is, I will like start with negative imaginary system theory. I will introduce its definition, the properties, its stability result, and then you would be really interested to see that is how this theory can be, or how the concept of classical control theory can be applied to multi-agent setting, and that can be applied to control these UGVs and UAVs and with the application of the security surveillance. Okay, with that, that is, as it is, I think already like 9:30 or even 9:40, I'm going to stop. But please like don't I think I had a like lot of things to continue, but I thought that is, if I like, go in a bit slowly by explaining each and everything, then the audience would, it would be easier for the audience to understand, because at the audience are from the mixed background, so that's why it took a long time. So for that, I really apologize. So I believe that you have at least understood whatever that is we have discussed so far. If you have any question, please feel free to ask me.
Hello.
Hello. Yes.
Sir, is it possible to share one or two research paper of yours related to this class? So it will be easier for us. Or if you can tell me the name of the paper where
Yes,
we
yes,
find that.
yes. Yeah. May I show that if you just go to my Google Scholar, that's momentarily just I can open that page and then from that you can easily get the information. May I open?
I think organizer can.
Just I'm going to show you the. So this is the, if you go to Google Scholar and type Parijat Bhaumik, then that is you would like you will be able to see the papers, and that is the negative imaginary system. That is the main research area. So there you will find some papers. But if you just wish to know the basics of the theory, then you can always see the first few papers published by Professor Lanzan and Ian Peterson in 2008. Anyway, they are like very renowned papers. So they were published in IEEE Transaction and Automatic Control. You can see that papers, and always please feel free to keep in touch with me. That is because during the presentation, I couldn't mention all the references because I haven't yet started. In the next presentation, I will start that theory. This is very interesting. I believe all the participants would be there on Friday as well. So then that is I will discuss the nook and corners of the theory and I will show the applications. Okay.
Okay, sir. Definitely, definitely. Okay, sir.
For the time being, that is, if you are interested, you please go to there's a Google Scholar to check some of the papers, or even that is, if you wish to know the basics of negative imaginary theory, just in the Google, you type the negative imaginary system theory or what is a negative imaginary system. You will be getting plenty of easygoing materials. Okay. But don't worry, in my next session, I will be taking all of them.
Okay, sir. Thank you.
Thank you. Any other question? That is, I hope there is Pratusha and
Hi, sir.
Anuradha,
This
you
is
were like,
Dr. Shilpa.
yes,
Am I
yes, please.
audible?
Yes.
Yes, yes, you
Yeah,
are
yeah.
audible. Please
Please
continue.
ask. Mhm.
Okay. Sir, it was a very informative session and it was a very detailed session. Though in
Thanks a lot.
just
Thank you.
60 minutes, it's very difficult to get to know all the complex things.
Actually, this
But
cooperative
yes,
control is really very vast subject. So that's why I felt like
yes,
that is okay. In the first session, if I can make a good platform of cooperative control, then in the next session, the audience will enjoy. Because otherwise, if I directly would have delved into this negative imaginary theory and directly they are designing the cooperative controller, it would be too hard for the participants, because I believe that is the participant, maybe some of them are from robust control background, but mostly may not be. So actually this topic comes mainly from the robust control. So that is the reason why I thought that is I should first develop a background or a platform so that after that the
okay.
audience
You
can
just
enjoy.
refer. Okay, you just refer to one of the paper of in 2008 um,
Ha. Okay, so
of
should I open that
Peter
one
and
then? Ha ha.
no. I'm just asking, is there any base paper which we can link with the theory and in which we can get the maximum
Yes, yes.
information?
In 2010, there was an survey paper by Professor Lanzan and Peterson. It was published in IEEE Control System magazine. That
Okay,
paper I can share. Okay, I can share with Dr. Anuradha, and he can share with all the participants. That was the
that would be
first
great
survey
because
paper.
we can,
Huh.
yeah,
Yes, yes.
because
I will
that
do that
would
today only. Huh.
really
That
help
is,
us
huh.
to. Okay, thank you so much. Thank you.
Yeah. I hope at least the cooperative control part is now fine for all of you. That is, what do you mean by multi-agent system, cooperative control, and then the related parts?
If I give you the honest answer partially because I'm not from the same background, so it took me like
Okay,
couple of
okay.
minutes to understand the concept. But
Huh.
yes,
Oh,
the
I believe
presentation
from
was
those
very
two
nice and very
experimental
informative.
demonstrations, it was a bit easier, right? When you see the robots that's moving in a particular fashion
Yes,
in a
yes,
geometric
yes.
shape. That is the
Yeah.
reason, that is why I started the presentation with those two like video.
Yeah, that is basically the best part through which we can understand the concept, because we are not from the same background. So making the
Ha, ha.
presentation more informative through the images and all that, that will help us to get the information. But yes, at the end, I would say that it was really an informative and a good presentation.
Thank you so much. Thank you. And in fact, that is as the audience from a mixed background. So the next day, I will also name the application in the other engineering disciplines. That is where you can apply this concept. I think here, there's many people are from CAC background or EC, right? So for the CAC people, CAC researchers and the students, the robotics is now an interdisciplinary concept or a discipline where the CAC people are doing a really like brilliant in the robotics domain. But apart from that, if you think about the mobile sensor network, the placement of mobile sensor network, there also, that is where I believe both CAC and EC researchers work, they also use the concept of multi-agent. And in fact, this kind of like the cooperative control or these kind of analysis things, they are widely used in mobile sensor network. Next day, I will name a few applications by which everybody can relate that is okay. This is not linked to only electrical engineering or control. It has applications in other domain as well. Okay. Any other question?
Sir, I have a small request.
Yes, please.
Can you just link your concept a little bit with the
Hmm.
management background, if
Yes,
it is
that can also
possible?
be possible. Okay, that before the next
Because
day,
I am from the
that
management background, so I just wanted to understand how this concept can be applied in our area and how well it can be accepted. So, if you can just relate it with the management, that would be great.
okay, okay. Thank you, madam. Thank you. Because that would be a new area. I will think and I will try to like share this my concept. Although that is I never saw any kind of paper on that particular one, but I will try to relate and I will make like a few slides on that. I believe that will help you. And in fact, it can be a very good research area also.
Okay, thank you so much.
Thank you, madam.
Any more question from the audience? I would personally like to thank you, Parijata, for the wonderful presentation, because you know that it's the efficacy of a presenter who has attracted audience of this vast domain and varieties of knowledge. As Dr. Shilpa said, she is from management background,
Ha,
and the
ha.
way she is asking you the questions, that means she has the interest to listen to you, and obviously the thanks and the credits goes to you. And I don't think that 2 sessions are sufficient enough to extract the knowledge from you, so we have to wait for more FDPs to listen from
Thanks a
you.
lot. Thanks.
Yeah.
But you know, that is
And
like initially I didn't plan in that way. But when I started and I could see that is at that time there was almost 87 participants. So immediately I could figure out that they must be from the different background, versatile background. So then I changed my mind. I started the presentation in a tutorial way. But when it ended, like when I got as the clock is continuously ticking, now that is I'm personally not very happy because what I like
exactly
planned to
the same
cover,
with
I couldn't.
the same with us, because I was also thinking that why the topic is getting, I mean, ended in an abrupt way. We are waiting to listen from you much more in this session, but we cannot go beyond the, I mean,
Ha,
assigned
because
time
like you might have seen
allocated.
that is I was only that is on the 23rd, the slide number 23, but like for today's presentation only I had 52. So that is I
Uh,
couldn't go into the application part anyway. That is next day I
it's
believe
our
now as the
impossible.
platform is ready, next day people can enjoy
Yes,
and I
yes.
can even like raise my speed a little bit.
Now, at some point of time, I was like thinking that why won't, I mean, we are not able to give you some chalk and board, because the way you are
Always like I like the offline presentation. Actually, when like Anuradha first she contacted me, and I was like requesting her again and again. That is why can't you make it an offline? That is I would just go there and I would be teaching with the chalk and board. But I know like there are always like there are some other administrative issues. But anyway, had it been a classroom session, it would have been the best.
Yes, of course, and we are actually waiting to arrange such kind of seminars or conferences in near future, and obviously we will be lucky to have you over there also.
Sure, sure. It will. I will also be like very happy that is if I get a chance to go there in person and like see
Pratyusha
you
ma'am, I
face to
just
face.
wanted to Pratyusha
Yes,
ma'am, I just wanted to say one thing, that at the end of the day, at this time, if from a diverse background, if you can link with the session and you can enjoy, that means that the presentation is really informative and interesting. So it's
Thank you, madam.
commendable.
So lots of honor, lots of honor.
yes, it is. It
Also,
really from,
may I
yeah,
ask one
it
thing? Actually, it is not relevant in this your class, but after seeing the class, I am just asking that. I used to see the robo war that is actually happened in Korea, Japan, and that countries. Robo war actually, a robo car. They are fighting
Yes,
each
yes.
other. So after seeing this session, this question is actually striking in my mind. There should be an control system based, na? So what kind of that
Ha.
control system actually working in that situation? That is very much tough.
Yes,
Is it
yes.
possible to enlighten in your next session if you can explain a little bit?
I will just give the audience some glimpse. Okay, I will give some
Mhm.
audience. Like, thanks for that question. I will, of course. Huh. So these two things, that is, as you like mentioned about this just robo car race, and Dr. Shilpa mentioned about the how we can whether we can apply these to the management
Not actually the
domain.
car race, actually, sir. The robo war. Actually,
Hmm.
one robot is fighting with another one. It is a
Hmm.
wheeled robot, and how they are balancing each other.
Hmm.
Okay,
Hmm.
because the surface is limited. How they can
Ha.
identify the surface limitation? Actually,
So there, that is like if you just ask me, that is what type of controller do they
yeah, yeah.
use? Like one is the like model predictive controller, MPC is one like very famous, and also the reinforcement learning based controller. So those two things are really very popular. That is, although that is I don't work in that area, but if you have to, like, if your agents are placed in a completely dynamic environment where it has to fight against others, and there can be any type of unwanted situation which are not deterministic in nature, in that way, the control scheme which now I have been explaining, these are all deterministic in nature, but under that kind of circumstances, we need the stochastic things. So for that, the MPC and even reinforcement learning based controller, the RL based control, those things would be really very helpful. That is the main difference between deterministic control and stochastic control.
Okay, sir.
Thank you for the question. It is really very important thing. Anyway, that is the next session. That is, I will take up both these issues.
Okay, okay, sir.
so thank you, Dr. Bhumi. And we are happy that we will be having you in another session of this FDP. So our
Tha-
participants have thoroughly enjoyed, and they are eagerly waiting to meet you for the next session. With this, I would like to call it a day. Thanks again, Dr. Bhumi, for the lucid presentation and attracting the participants from all different backgrounds. This is
Thank
one
you
of
so
the
much. I am also that it was my great opportunity that is I could like share like my research work or even this topic with like the so many participants, and that too from different backgrounds.
Thank you so much, and thank you, participants. And the link for the feedback for this session would be shared to your WhatsApp group very shortly after closing of this session. And you are requested to upload the feedback forms by tonight. So So thank you once again. Good night. See you
Thank
all
you.
tomorrow, 6 p.m. Thank you,
Yeah.
Parijatta, and good night to all the
Thank you,
participants.
Pratyusha. Thank you.
Thank you, sir.
Thank you.